So we are going to discuss the work in a thermodynamic process. As I told you in the last discussion that we will be discussing the relation between Cp and Cv. So this we will be doing after discussing the first law of thermodynamics. So first of all, let us discuss what is the work in a thermodynamic process. As you know that for a system, work done is equal to the force multiplied by the displacement during a process. dW is equal to this. So suppose we have this system which contains the piston and the cylinder arrangement, and it moves from this point to this point when certain pressure is applied on this. So the area of cross section of the piston is A, and this moves through a distance which is equal to dx. So it contains an ideal gas. This is our system. This is the system boundary. When you heat this, the energy of the molecules is increasing. As a result, they will apply more pressure on this piston and on the cylinder walls. This boundary is movable, so it will move, the others are not movable. So what is the force acting here applied by the system on this? On this side we have atmospheric pressure which resists the movement. So on this side the pressure must be greater than this, that's why this is moving in this direction. So pressure into area is the force. So dW is PAds. What is ADS? ADS is this space, the volume swept by the piston while moving from this position to this position. ds, area of cross section is A, so this space is A into ds, and this is equal to dV, the change in volume, PdV. So work done is equal to PdV in thermodynamics, and for a complete process the work done is integral of PdV, and this formula we use for a reversible process. That means a process which is during which the system is in equilibrium during the entire process. This is a reversible process, this is an ideal process which actually does not occurs at infinitesimally slow rate. This is how we define a reversible process. And after the process occurs, there is no trace of it is remaining when you take the process from the end point to the starting point again. So if I have this process occurring in this direction, point 1 to point 2, and you move back following the same path, then there is no change in the system and the surroundings. We reach the same initial point. I will give you an example of this. If I walk from one point to another point on this ground, this is not a thermodynamic process, but heat and work exchanges are involved. I walk from one point to other point. So what I am doing here is doing work against the friction. Not doing work against gravity, but doing work against the friction. If I walk from the end point to the starting point again following the same path, there is no deviation in the path. So the question is, will I get the work I have spent against the friction during this? The answer is no. Answer is I will have to do more work against the friction. So I have to do the work, so friction is always present. Similarly, in case of the thermodynamic systems and the processes, friction is always present. So it means that the friction makes the process irreversible, non-ideal. So a reversible process during which system is in equilibrium everywhere, and these points can be retraced But if the process is irreversible, then you move from 1 to 2 like this, start from 2 to go to 1 again, you will reach this point 1 dash because of the friction. So this is irreversible process. And for an irreversible process, work done is P delta V and not integral of P dV, because integration cannot be carried out during a path which is not in equilibrium. So this is the formula we are using for the purpose of calculation of work during a thermodynamic process. Let us take an example of, say, the adiabatic process. So work done is P dV integral, and P and V must be related for this. For this type of work, P and V must be having a relation with each other. So here I can write P equal to C by V gamma, put the value here, and V1 to V2, initial to final volume. So for this process I have this relation. This will be followed at every point during the process. This is say point 1 and this is point 2. So during this entire process, in whichever direction it may occur, if the system is expanding like this, system is doing work against the surroundings. If the system is being compressed, if I apply a force like this and the system is compressed, then work will be done on the system, that will be negative work. So I can write this work here is equal to C. Put the value of C, this value here, when you multiply this with V2, and this value of C when you multiply this with V1. So P2 V2 minus P1 V1 over 1 minus gamma. And you know that for an ideal gas, PV equal to mu RT. So this is mu R T2 minus T1 over 1 minus gamma. This is the work done during an adiabatic process. And during a process, the work done is given by the area under the process, area under this curve. So if you take a small element here, the change in volume is dV, and the value of pressure here is P. So P into dV gives you the area of this small element, almost a rectangle. So integral P dV for this continuous path, work done. So work done is defined as the area under the process, area under the curve of the process. So this is the work done for an adiabatic process. Now we can find the work done for an isothermal process. For isothermal process, the equation is PV equal to constant. So W is integral of P dV. Put the value of P, C by V dV from V1 to V2. This is C log V2 by V1, or C is, I can write P1 V1 equal to P2 V2 equal to mu RT. T is constant, equal to C. T1 equal to T2. If this is the process, temperature is constant for this, or PV equal to constant 1 to 2 on all these points. So putting the value of C here, P1 V1 log of V2 by V1, or P2 V2 log of V2 by V1, or mu RT log of V2 by V1. In terms of V2 by V1, we can also write from this P1 by P2 in this equation, and this can also be written as 2.303 log to the base 10 V2 by V1 and so on. This is the work done during the adiabatic process. Means that the area under this curve, this will give you the work done during this process. These are two of these processes, and now we will be discussing after this the work done in other processes, thermodynamic processes. The other processes are isobaric process, for which the relation is pressure is constant. We have to find the work done during this process. And an isobaric process on a PV diagram can be shown like this. Pressure is constant, volume is changing 1 to 2. So the area under this will be the area of the rectangle. So W is P dV, P equal to constant. So C V2 minus V1 or P V2 minus V1. Here P1 equal to P2 equal to P. This is work done during isobaric process. And then we have isochoric process, for which volume is constant. That means dV, change in volume, is 0, and integral P dV means work done is 0. Or in other words, you can see that the area below this curve is 0. This is a straight line. There is no area below this curve. So work done during an isochoric process 0. As there is no change in the volume, so there is physically no movement of the piston or no movement inside the system, inside outside. So that means the work done here is equal to 0. This is how you calculate the work done in different processes. If suppose, for example, it is given that the pressure and volume are related as linearly, P is equal to A plus BV. A and B here are constants. You have to find the work done during a process of expansion. The system expands from state 1 to state 2. P and V are related as per this relation, and the relation is a linear one. So you can draw this relation. This will look like this. So if you move from this point to this point, you have to find the work done during the process. When V is 0, P is equal to A, and when P equal to 0, V equal to minus A by V will be negative. If you plot this, V is 0, P is equal to A, and when P is 0, V is negative. This will be the process. So we have to find the work done during this. So this is integral of P dV. Putting the value of relation in terms of V, P is A plus BV dV from V1 to V2. This is 1, this is 2. V1, V2, P1, P2. So this is A V2 minus V1 plus B V2 square minus V1 square divided by 2. This is how you can find the work done during a process which is a reversible process, which is in equilibrium at all the points, intermediate stages, and for which the relation between P and V is given.